Hi, I'm Jamie, and today I'll talk about unsupervised change detection for space habitats using 3D point clouds. This work presents an algorithm that detects anomalies in space habitats. Using robots to detect changes in the environment, we can alert astronauts and other operators to potential hazards, such as blocked vents and free-floating cargo. We can also improve the internal environment map without having to update the entire map each time. Anomaly detection is critical for robotic tasks such as mapping, surveillance, and inspection. Map creation is resource intensive, so only updating the parts of a map where changes occurred improves efficiency. Surveillance is necessary to detect threats and obstacles in an environment to robots or people, such as finding changes which could create fall hazards. Anomaly detection can also be used in fault detection and isolation architectures, such as in factory settings to remove out-of-spec components. The robot used in this work to advance anomaly detection is Astrobee, a cube-shaped free-flying mobile sensor platform on the International Space Station, or ISS. In the image on the right is astronaut Anne McClain with Astrobee on the ISS. The image on the left shows all of Astrobee's sensors and components. In this work, the HazCam and NavCam were the two main sensors used. The HazCam is a picoflex time-of-flight depth sensor from which we collected point clouds, and the NavCam is a wide field-of-view color camera used for localization and map reconstruction. Most related works relied on using 2D RGB images for scene change detection. One method that this group researched was using a series of 2D frames and a 3D reconstructed map as input, and highlighting change ellipses on the map as output. Other methods, such as one that combines global semantic and local geometric information, relies on manual data labeling. Additionally, all of these methods suffer from sensitivity to lighting conditions. A third algorithm uses point clouds of the scene, summarized as Gaussian mixture models, to compare the environment between times to find changes. However, the paper only demonstrates success with single added objects. This SciTech work extends this algorithm. In addition to single added objects, this work can detect both multiple added or removed objects. Testing was done with the Astrobee in the Granite Lab, which is an environment that simulates the conditions of the International Space Station to test the algorithm in a space-like environment. Finally, the code is released publicly on NASA's Isaac Git repo for further development. To give a brief overview of the pipeline, we see the same corner of the scene in 2D and point cloud images taken by the Astrobee with and without a cargo bay. The point clouds are then summarized into Gaussian mixture models, theta T0 and theta T, which are then used as inputs to the final change detection algorithm that extracts the Gaussians associated with change regions pi. Clustering is done with an expectation-maximization algorithm. In the expectation step, we find the probability that every point belongs to every cluster, and in the maximization step, the parameters and weights are updated to maximize the likelihood that each point is assigned the correct cluster. However, the classic EM algorithm assumes the optimal number of Gaussians to use, k, is known. Since k is unknown, it is initially overestimated, and the M step is modified to iteratively reduce the number of Gaussians by removing clusters with too few points associated with them. An example of the algorithm fitting randomly generated data is shown on the right. Earth mover's distance, or EMD, is the metric used to determine how different two sets of GMM distributions are. EMD is the amount of work, or force times distance, necessary to transform one set of distributions into another. Imagining that one set of distributions consists of piles of dirt, and the other, holes, the EMD is the amount of work necessary to fill all the holes with dirt. In this representation, the Earth, or force, is the weights of the distributions, and the distances are the distances between every distribution mean. This figure shows the change detection part of the pipeline. First, the point clouds are clustered into GMMs, which are used as input to the change detection pipeline. Next, the EMD is calculated between the two distributions. If the EMD is above a change tolerance threshold, the Gaussian from the after GMM that contributes the highest degree to the EMD is removed from the after GMM to the final change GMM. This process repeats until the EMD approaches 0 or is below the threshold. Finally, the change GMM is overlaid upon theta T, the after point cloud, to highlight the changes in the scene. This is the Granite Lab at Ames Research Center where testing was done. The Astrobee glides on the granite table, shown in the image on the left, using an air-bearing system that allows it to glide with 3 degrees of freedom. On the right is an example of the path Astrobee takes during a pre-planned survey of the lab. Here is Astrobee during one of the data collection surveys. Along the back wall are a cargo bag and a second Astrobee, which were objects added to the scene. The video on the left is actual Astrobee sensor data collected with the navcam, and on the right is a simulation using the collected localization data to replay the same survey. This is an example using single-frame data with an Astrobee added to the scene. Clustering is shown in the center, with the Astrobee highlighted in teal. The Astrobee is detected in the rightmost figure, again in teal. However, artifacts are seen from misaligning the search boundaries of the point clouds, causing false positives near the edge. Here are the results using the entire scene as input, with an Astrobee and cargo bag on the leftmost wall, and clustering of the scenes in the center. There is again a false positive near the boundary, but changed Gaussian successfully cover the Astrobee and part of the cargo bag. Now here are 3 objects in the scene, GMMs again in the center. The Astrobee detection was a little off the mark, but the cargo bag and crate were clearly detected. These are the performance metrics across a single frame, 1 object, and reconstructed map, 2 and 3 objects cases. Accuracy of the 1 and 3 objects cases were the highest, possibly because the objects were close together in the 2 object case. The 3 objects case had the best precision, and the 1 object case had perfect recall, possibly because in the single frame, the object takes up a large portion of the search area, especially compared to the reconstructed map input. Finally, the overall F1 score was the best in the 3 objects case, meaning it struck the best balance in precision and recall. One tunable parameter in this algorithm is the maximum number of k Gaussians. Though the EM algorithm was modified to select k autonomously, the algorithm is subject to overfitting. When k is too small, k equals 10, the objects tend to cluster into the environment. With a very high k value, the objects become increasingly fragmented, which is a poorer summary of the data with a worse runtime. The optimum number of Gaussians for reconstructed maps was around k equals 25, where both objects are detected and clustered into just 1 or 2 clusters. In another experiment, the data was pre-filtered with principal component analysis to remove a dimension of the point cloud data and improve runtime. With the Granite Lab, since the z-dimension is practically uniform, PCA essentially flattened the data along this axis. In experiments using reconstructed maps, this step reduced runtime by about 10%, but may not be feasible in more complex environments, such as the ISS. Computation time was computed and broken down according to algorithm step. Far and away, the most computationally expensive task is the clustering algorithm, which takes over an hour with k equals 25 clusters on the full scene. Optimization of this step and setting the number of Gaussians of the GMM once a reasonable size has been found for the environment in subsequent remappings would reduce runtime significantly. To build upon this work, simultaneous detection of appearances and disappearances should be implemented. Optimization of k initialization and point cloud filtering would also improve runtime and results. Finally, testing on the ISS is the next step to determine how the algorithm handles the increased scene complexity, which can be seen in the image on the right. The change detection pipeline detects new or missing objects, such as the cargo bag example on the right, without requiring painstaking manual labeling of data, and is insensitive to lighting conditions. Multiple object detection was demonstrated, with the code released publicly on NASA's AIAA codebase on GitHub. Work with Astrobee in the microgravity simulated environment of the Granite Lab also demonstrated potential for use in space-like habitats and environments. Thanks to all the people in or associated with the Intelligent Robotics group at NASA who helped with this project. Thanks as well to all of their respective organizations and sources of funding for sponsoring their time with this project. The paper with more details can be found using the link or QR code shown here.